Good. Okay. Thanks everybody for sticking around for the last session today. So I'm going to get us started with a review talk about instrumentation as it relates to understanding how planets form and evolve. I'm really excited to be here. I was actually a PhD student here at U of A, and so Tucson has a special place in my heart. I love coming back to visit, and I'm excited to talk to you all. So this will be kind of an overview that's not going to be comprehensive by any means, but I will try to hit some highlights for cutting edge instruments that help us understand this process. So I'm going to start with a version of a figure that we've seen many times in exoplanet talks that might be a little bit different from the standard one. So what you're seeing here are confirmed exoplanets as of a couple of years ago in gray points. You have mass and semi-major axis here. And then disk features are the colorful points here that may be indicative of embedded planets in protoplanetary disks. And so the location of these points shows you the inferred planet masses and orbital semi-major axes from observations of protoplanetary disks. And there are many things that you could take away from these data sets in this figure. I'll just highlight a few of them. One is that if you just focus on the exoplanets for a second, you can see that the gray points don't overlap with the solar system planets, which are these black rectangles. So, you know, we haven't quite gotten there in terms of detection capabilities to reach planets that are in our own solar system. We can also see that given our current resolution and sensitivity, we are detecting more and more disk features that indicate the presence of planets that are at our instrumental limits. And so basically, like as we push our instrumentation capabilities, we're expecting to continue to fill out this parameter space and expecting to be able to see disk features that can tell us something about planet formation as it relates to lower masses and even tighter orbits. So this is, you know, big picture motivation for basically pushing our mass sensitivity and our spatial resolution across the board for upcoming instrumentation. So just to kind of spell out some of that big picture motivation for future instrumentation goals, here are some non-exhaustive goals for observing planet formation and evolution. One is to build a census of characterized exoplanets, so spectroscopically characterized exoplanets with a broad range of ages and properties, including small rocky planets. So this includes obtaining mass measurements from RVs and astrometry. It also includes atmospheric measurements from transit spectroscopy and direct spectroscopy. And we want to do this for a wide range of planetary systems. So this includes doing things like mapping protoplanetary and debris disks for a wide range of orbital radii and ages. And of course, there's a whole bunch of stuff that I've left out here, including important solar system observations of planets and small bodies, interstellar objects, exomoons, exocomets, things that we've heard a lot about this week. And so in terms of techniques, there we go. Some of the techniques that we're going to highlight today include indirect observations like radial velocity and transit observations and spectroscopy, direct imaging and spectroscopy of exoplanets and disks, and also interferometry at a wide range of wavelengths. And so my own background is in instrumentation related to direct imaging and spectroscopy and interferometry. So just disclaimer, this talk is going to be heavy on that stuff because that's what I'm well equipped to talk to you all about. But we will touch on these guys also. So before we go through some instrument highlights, I figured I would just talk about some technical considerations and goals for kind of current and future instrumentation. And so if we're thinking about observing exoplanets and disks, contrast and sensitivity are really important. I'm preaching to the choir here, but exoplanets and disk features and other spatially resolved objects we would try to observe are generally faint. Things that orbit stars are faint compared to their host stars. Transits are shallow. So all of this motivates wanting high sensitivity and high contrast. You can just see an example of some very simplistic SEDs of planets here. And you can see that flux ratios between planets and host stars can be very, very severe. And so I'm just laying out a few examples here. For forming planets, we might be okay with contrasts as low as 1 to 100. But if we want to actually characterize rocky planets around nearby stars, we need to get down to 10 to the -7 to 10 to the -10. In terms of sensitivity, just if you do like a quick back of the envelope for how many photons you would expect to receive from a rocky planet, say at J band, you could be looking at something like a handful of photons per second. So this motivates large apertures and high throughput. So some goals here are maximizing throughput, minimizing and mitigating optical imperfections, and developing post-processing strategies to actually achieve rocky planet contrast. So there's a lot that goes into that, and I will just touch on a couple of things that are important on the high contrast imaging side, and one is suppressing starlight. So we use adaptive optics to accomplish this. This is where you measure the blurring effects of the Earth's atmosphere using a deformable mirror, and then correct for it. And so I'm showing a couple of examples of deformable mirrors over here. They can be really small and really far down in your optical path. They can also be really large, like the adaptive secondary mirrors here at the LBT. And this animation just shows you something about how this works and what the image correction looks like. So here you can see the wavefront as it's entering your telescope. Here is what a DM might do to correct that wavefront, and then these are the residuals. And over here is your kind of high time resolution movie of what your image looks like beforehand. And here's what it looks like after. So AO is one step in kind of concentrating your starlight so that you can then suppress it in some way. And so you can see that your image here is much sharper than before you've used your adaptive optics system. And so often when people are looking to take direct images of exoplanets, they'll couple adaptive optics systems with coronagraphs. And so you can see a couple of examples of the starlight suppression you can do with different coronagraphs here. So one very famous example is the vortex coronagraph, where you put basically a phase ramp at the focus of your optical setup to null the on-axis light. So before you might have an image like this, and then after you have images that look like this as you tune up the alignment on the coronagraph. And then there are also more maybe fancier versions of this where you use phase variation in actually the pupil plane of your setup to actually null starlight in certain locations of your image. So you might have heard of digging dark holes using phase apodization coronagraphs. So these are just some of the technical components that go into doing this. And in the end, we arrive at contrast curves that look something like this. So this tells you how faint a planet you could actually detect compared to your host star. And here's a typical example from Keck. And so you can see, this is with Keck NERC2 at L band. You can reach contrast of something like 10 to the -5. And there's a lot of work going on right now that's going to push this down to something like 10 to the -7 in the coming years. And we'll take a look at that toward the end of this talk. Just a couple more technical things before we just look at some instrument highlights. One is spectral range and resolution. So different wavelengths and spectral resolutions are going to be suited for different, or better suited for different science goals. So the big picture goal here is to have a wide range of spectral resolutions over broad bandpass. A couple of examples of optimizing here are, for example, if you wanted to detect cold planets in direct imaging, the colder you get, the more of their light they're going to emit in the thermal infrared. So you might, for example, design an instrument to operate between 3 and 5 microns if you want to get down to a few hundred Kelvin. Similarly, if you're thinking about atmospheric composition and atmospheric physics, different wavelengths are going to access different physics in exoplanet atmospheres. For example, UV is going to show you details about atmospheric escape, whereas clouds and hazes are going to be more easily detected in the infrared. All right, and the last one is systematic errors, and this is like a big catch-all for everything that could be a surprise that would limit your detection capabilities. And so here I'm just highlighting a couple of potentially familiar space-based examples. Detector systematics matter a lot for things like photometry and for direct imaging. We've seen this with, for example, Spitzer pixel sensitivities. So you can have different photometric sensitivity across a pixel that can affect photometric observations. You can also have thermal drifts that affect your photometry and point spread function. And this is, kind of an easy example here, an early observation of a tilt event when one of James Webb's mirror segments tilted and then affected an exoplanet transit signal. So calibrating these things and minimizing them is another goal when you're thinking about instrument design and post-processing. Okay, so that's kind of a grab bag of technical considerations that matter. For the rest of the talk, we'll just go through some highlights from recent and near future direct imaging and spectroscopy instruments. And so what I'm going to try to do is kind of, this is not going to be comprehensive for every instrument, but I will try to tell you kind of the unique technical aspects of each one and highlight some of the recent science results. So I'll start with an instrument that's close to home here in Tucson, which is the Magellan AO or MagAO X. So this is the upgrade for the MagAO system. You can see a CAD drawing of the instrument over here. You have two optical benches, and I'm not going to go through all of this, but the important parts are that you actually have three deformable mirrors here that allow you to do kind of low spatial scale correction of your images, fine spatial scale correction, and then to try to minimize any non-common aberrations between your science instrument and your earlier wavefront sensors. So this is your pretty CAD drawing. This is what a picture of the instrument actually looks like. So they're always busier than these clean things. And something that's unique about MagAO is that you can observe in spectral differential imaging mode, in particular at H-alpha wavelengths. So this is the hydrogen alpha line. You can observe simultaneously on the line and on continuum to isolate H-alpha signatures like accretion onto forming planets. And so this is a cool recent result from Jialin Li, who's actually a grad student here, detecting an H-alpha bright companion, which you can see here and here, inside a gapped protoplanetary disk. And so there have been a lot of cool results coming out of MagAO related to planet formation physics, thanks to this observing mode. For the next couple of slides, we'll focus on these kind of extreme adaptive optics systems and what kind of direct imaging we can do with them. So the Gemini Planet Imager and the upcoming upgrade, GPI 2.0, are what you can see here. GPI is similar to MagAO in that there are multiple wavefront sensors and deformable mirrors that allow you to get really high STREL. This has shown us cooler exoplanets, like giant planets with temperatures of something like 600 Kelvin, like 51 Re-B, which you can see here. Something that's somewhat unique about GPI is its polarization modes, polarimetry. So there have been a lot of beautiful debris disk mapping results to come out of GPI. And then if you want to look at this block diagram of upgrades between GPI and GPI 2, you can. Basically, they're upgrading all sorts of high contrast components like coronagraphs, the wavefront sensors, the software that will push contrast down to something like 10 to the minus 7. I'm kind of lumping together a few extreme AO instruments on this slide, just to kind of highlight some planet formation capability or observation capabilities. So this is a highlight for SPHERE and MUSE and NACO, all at VLT. There's a CAD diagram of SPHERE over here, where you can do optical through infrared imaging and integral field spectroscopy. So you can actually get spatially resolved spectra for things like disks around young stars. And these instruments together gave us a really clear picture of the PDS-70 system, which is kind of like the poster child for planet formation. And one important takeaway from this is that These papers and these observations really have highlighted the importance of multiband imaging for understanding what's going on around young stars. If you just went with infrared continuum, you see two blobs where PDS-70b and C are. You might wonder, like, is this actually just a disk feature? I'm not sure if this is like a self-luminous companion. But when you add the H-alpha observations, you can firmly identify forming planets in this system. So those are a few examples of imaging and low resolution spatially resolved spectroscopy on kind of like 8 to 10 meter class facilities. There are also ongoing instruments and upgrades to do high spectral resolution observations of planets on these large telescopes. So there are a few names of instruments that do this up here. The basic idea here is that you can couple a fiber-fed spectrograph with your adaptive optics corrected instrument to inject planet light and get R of something like 100,000 spectroscopy. So you can see a diagram of how this would work up here. And what you actually do with these data are get your raw data from the spectrograph and cross-correlate them against model atmospheres to look for signs of molecules, for example. So you can see a few science highlights from the last couple of years related to these instruments. So this is from HiRISE. These are direct water and methane detections for, I believe this is AFLAP-B. Yeah, so this is a mass-constrained object that was first identified with astrometry. And then you can also do things like indirect spectroscopy, where you're, for example, observing transits or eclipses of transiting planet systems. And this is an emission line observation of CO in WASP-33b. So this kind of high spectral resolution spectroscopy of planets can be used in the future to look for things like biosignatures, for example. Okay, I'll take a couple of minutes to talk about LBTI, since this is a facility that I spent a lot of time with as a grad student. So this is on the Large Binocular Telescope on Mount Graham here in Arizona. And LBTI actually co-phases the light from the two 8.5 meter mirrors on the Large Binocular Telescope. So you can see a diagram of how this works over here. You have two wavefront sensors, one for each primary, and then you phase up the light between the two primaries, and you can do things like null the central star. You can do imaging from 3 to 5 microns and actually also spectroscopy across that range, and somewhat uniquely mid-infrared imaging. And so LBTI was kind of originally set up to do things like look for exozodi around nearby stars. And so you can see an example of constraining the frequency of exozodiacal dust around different stellar types over here. This has been important for planning for future observations where you would search for Earth-like planets where exozodi might be contaminating things. It has also been used to map lava lakes on the surface of Io. And you can see a cool example of doing this when Europa actually occulted Io. And this allowed people to like spatially resolve lava lakes and find new features on the surface. Ongoing upgrades at LBT include improving the co-phasing camera so that you can actually co-phase on fainter stars. This expands sky coverage, and developing new detector setups for mid-infrared imaging, and that's being pushed by Brittany Miles, who's here. One last science highlight is that interferometry on LBTI has also helped us look at like the inner few AU regions around young stars at a few hundred parsecs. So you can see an example of an outflow cavity around one of those here. So interferometry has been really productive for exoplanets beyond just imaging. Astrometry and spectroscopy have come out of gravity on the VLTI, and this gives you resolution up to baselines of like 140 meters. So the astrometric precision is something like 50 to 100 micro arc seconds. So this is really impressive. All of this happens on a silicon etched chip over here. This is where the light actually gets interfered. And so people are using technologies like this to kind of miniaturize pieces of instruments, and Gravity and its upgrade Gravity Plus are a cool example of that. Okay, so those have been ground-based highlights. I will spend a little bit of time on James Webb before wrapping up. So of course, now we have this amazing, super sensitive space-based imaging and spectroscopy capability with Webb. And this has really pushed our sensitivity in terms of planet temperatures. So we're detecting planets on wide orbital separations, like these two examples here. This is EPS Indi AB and 14 Hb. These have temperatures of something like 250 to 300 Kelvin. And we're getting down to contrast of something like 10 to the minus 6 out at wide angular separations. So this is kind of mapping our cold planets on wide orbits relative to our ground-based capabilities. People have also put a lot of effort into recovering planets in integral field spectroscopy with NIRSpec. This is kind of a busy slide, but the important takeaways are that we've been doing this by modeling the actual traces on the NIRSpec images, and including forward modeling of things like detector systematics and optical imperfections. And this helps us to recover spectra of relatively close-in low-mass companions. Okay. One thing that I'll just do a quick plug for, is that you can do interferometry with James Webb with NIRISS. So when I think about Webb, I often think about it like this instead of the field aperture. So this is where you put a mask in to turn Webb from your conventional telescope into an array of smaller ones. This gets you a boost in angular resolution. Your images look like this. Use post-processing to actually understand what's going on in your brightness distribution of your object. And this has recently located the PDS 70 planets at just like a couple of 100 milliarcseconds at 5 microns. And this has allowed us to make measurements of circumplanetary disks in the infrared around these objects. Okay, so in the last couple of minutes, I'll just talk about where we're headed. So in terms of really pushing contrast, we have great things to expect from Roman in the coming years. There's a lot of tech development that's going to advance the state of the art of coronagraphy and space-based coronagraphy with Roman. We're expecting to get down to contrast below 10 to the minus 8, thanks to multiple wavefront sensors, which you can see here, and software that lets you dig dark holes around your stars. An upcoming instrument that I'm particularly excited about is called SCALES. So this is a 2 to 5 micron integral field spectrograph that's currently being built for Keck. SCALES is going to get commissioned in 26A, and we can expect detections of colder planets than we can typically image from the ground, thanks to SCALES' longer wavelength coverage, which goes out to 5 microns. You can check out these papers for summaries of SCALES' big picture science impacts, and also how SCALES can help us image Gaia planets in the coming years. So I'm the project scientist for SCALES, so talk to me if you're interested in using a thermal infrared integral field spectrograph. I thought I would show you a nice picture of the instrument from like last week. It is actually closed up now and entering its 3rd test cool down. And you can see almost all of the components of the instrument here. There are a whole bunch of different gratings and prisms that you can use for different integral field spectroscopy modes. There will be coronagraphy, aperture masking, and all of it will Nyquist sample your image so you can do high resolution imaging. So chat to me if you want to use SCALES. And I will just end here, which is thinking about where we're headed in the future, which is now a much busier version of the contrast curve plot that I showed you at the beginning of this talk. Right now, we're kind of living up here in terms of our capabilities to image high contrast systems. So we're out at something like 10 to the minus 6, 10 to the minus 7, where our hot giant planets are. Thanks to advances in things like deformable mirrors and wavefront sensing and software, we're starting to push down to lab contrasts of 10 to the minus 8, 10 to the minus 9. We can expect to get there on a real instrument when Roman launches, and you can see some expected contrast there. And then in even further future instruments will get down to the contrast that we're going to need to actually characterize planets like the rocky ones in our own solar system. So thanks for your attention, and I'm happy to answer any questions.
Great. Yes, we definitely have some time for questions.
Thank you so much for this great talk and this really exciting capabilities of scales and other instruments. So I was curious, wearing my lab hat. We don't have a chronograph Genius high resolution IFU. Do you foresee synergy between scales and Genius? The high resolution is 19,000.
19,000?
Yeah.
Oh, that's great. Yeah, so I think there's definitely synergy there. So I didn't mention this. The highest spectral resolution modes for scales are of like 7,000 at M band. And so I think there's a lot of cool stuff that you could do with, medium spectral resolution observations with scales and like high spectral resolution with Genius. So one example would be, if you wanted to like observe hydrogen line profiles for like an accreting planet, for example, R of like 19 or 20,000 is like a pretty good spot to be in to actually measure line profiles that you could compare to accretion scenarios. So I think that's just one place where they're complementary, but I'm sure that there are other ones for, atmospheric characterization also. Yeah. Yeah.
Great. Any other questions? And if our next speaker could make it right now, thank you.
Thank you. Yeah, just to follow up on Cicero's question, what are the limitations or what are the prospects for spectral resolution? How much better can we do?
That's a great question. I know that the plans for upcoming high resolution spectrographs all kind of max out at like R of 100,000. And what I don't have a great answer to is how much you would gain by going past that for, for example, like atmospheric science. I don't know if that's a number that is kind of like, what's feasible. Yeah. That's right. That's right. Yeah, that's right. That's right. The kinds of like, PSF deconvolution you can do yep, that's right. Yeah. And the cross correlation stuff. Like, yeah, I think I don't know how much you would gain by going higher. Yeah. Yeah.
Great. All right, well, let's thank our speaker again.